Hello everyone, welcome to the video lecture in BK Math YouTube channel. Today I came up with the orthogonal functions, and we will see what we study orthogonal function, especially in Fourier series expansion. Let's try to understand what makes the very default method of Fourier series work. For the present, let's start with the real functions. Then we start our journey with the formal definition what orthogonal functions of the real valued function, especially so that we need not speak study with the orthogonality of vector valued function. For simplicity, we have been a little limited in our discussion, so we introduce the idea of orthogonality of the real valued function, and we show how the different variety of Fourier series can be treated in a unified fashion, so that the most important system of the orthogonal functions give rise to the trigonometric Fourier series, which we'll be discussing in the next section. So this is the precise definition what orthogonality of two real valued function. Two real valued function f and g are orthogonal on an interval AB. On this interval AB, if the inner product here is the inner product, we define the inner product to be the integral of the product here. The inner product here can be defined by the inner product of to be the integral of the product of f and g dx. If the inner product is 0, we call f and g are orthogonal functions. Orthogonal function. Most of you are more familiar with the orthogonality of vector, the orthogonal vector, so that this terminology is supposed to be analogous to the case of the ordinary vectors in their inner or dot product that we have been customarily familiarized with the dot product of u and v. If the dot product of u and v is 0, then u and v are said to be orthogonal or perpendicular each other. In the same fashion, you can also define the orthogonality of two really valid function via the inner product here. If the inner product, which is defined by the integral of their product, is 0, then intuitively f and g are orthogonal to each other. So that whichever you have been f g, then we can define through the inner product of the integral of the products f and g. And if this is 0, then we call f and g are orthogonal. So it's pretty easy to understand that making integration over the given interval AB, if f and g, after the making our integration, you can also adopt the techniques of integration, then you finally assign specific value at x equals to b, at x equals to a. Then if you gain 0, then f and g are said to be orthogonal. So no function is orthogonal to itself except the 0 function. Okay. When you come to the norm of function f of x on an interval AB, we define the norm of the function through here, and the square root of the inner product f with f itself again defined through the inner product to be the integral of this product, that means squaring dx. That's the norm of the function, so that it's possible to find out the norm of any arbitrary function on the given interval AB. Having this in mind, we can extend to the set that the orthogonal sets again we have f naught of x, f1 of x, f2 of x, f3 of x, any n number of functions in which the set is the set contains. So the set is said to be orthogonal on AB if individual functions to each other are said to be orthogonal. That means we have fn of x, fm of x, and from A to B, fn of x, m of x, dx is 0 for m different from n. Otherwise, cannot be 0 if m is equals to n. In this case, you mean the function is identical. So unless the function is 0, it could not be orthogonal to itself, you mean, like I mentioned it before. That's why we intentionally restricted m different from n. So if from A to B, fn of x, the product of fn, fm, dx is equals 0, then fn and fm are orthogonal, so that the entire set is said to be orthogonal set on it. Interval AB, if that's every individual function to each other are orthogonal on the given interval AB, you mean it's just straightforward that what orthogonal sets you mean. Simply check up the individual function f naught with f1, f2 with f1, or f2 with f naught, and so like, so that if they are orthogonal, that means if the inner product is 0, then the set is an orthogonal set. That means contains an orthogonal function, you mean. We have also the orthonormal set of f naught, f1, f2, f3, etc. are orthonormal on AB. The set is said to be orthonormal on AB if they are orthogonal. That means individuals over the AB, the indefinite integral of the inner product be the integral of their product is 0. If they are orthogonal, plus the norm is 1. We have already defined what norm is in the previous slide. So that if it's orthogonal, the set is orthogonal, and individual function has 1 in its norm. The norm is 1 for all n, you mean. So it's straightforward to define what orthonormal set, orthogonal set, and the orthogonal functions f and g, you mean. This is exactly what customarily to the ordinary vectors you have been addressed in vector. So I think it's better to develop the idea through instances. We have this example, the first example, the functions f1 and f2. f1 is x, f2 is x squared, are orthogonal on AB where a less than b. If a is minus b, you mean. So it depends on the interval. f1 and f2 are orthogonal on this interval if a is minus b, otherwise cannot be orthogonal on the given interval, you mean. That's why it depends on the interval AB. So we need to prove this with the help of the definition of orthogonality. That is, when a less than b, the orthogonality of x and x squared mean we define via the inner product from A to B. X times x is x cubed dx. Then looking for the integration using power rule. That's exceedingly elementary to apply here in this section. The 4x4 over 4, I mean, because demi-variable x, then you assign specifically at x equals to b, at x equals to 4, I mean a, then 1 over 4 b4 minus a4, and this can be expanded or factor out as a square minus b square, a square plus b square. Clearly, if a and b are not equal, because if a is less than b, if a is less than b, then a square plus b square cannot be 0. That's obvious. Because a is less than b, then a square plus b square could not be 0. Had it been a is 0, b could not be 0 because b is greater than a. So the only option we have here is 1 over 4 a square minus b square, a square plus b square is 0. The last brace expression here is not 0, so we have only a square minus b square is 0. The underlined brace, this expression is 0 on it. Why this is not 0 always? Because we have a less than b. So for a less than b, a square plus b square cannot be 0. Sorry. So this leads to have a square minus b square is 0 again. You can factor out a minus b, a plus b is equal to 0. A minus b is not 0. Why? A is not equals to b. Had it been a minus b is 0, you say a is equals to b, so which is contradicts with the premises. So a plus b is 0. Okay, this is 0. So if a plus b is 0 mean a plus b is 0, then you can move b to the right side. A is minus b, hence it's just prove it. So these functions x and x square are orthogonal on a b where a less than b. If a is minus b, you mean the two functions are orthogonal, which are dependence. The orthogonality depends on the interval. You may. One more instance, we need to show that this set is an orthogonal set in the minus pi or minus pi. That is 1 cos x sin x cos 2x sin 2x cos 3x sin 3x and so like. This is an orthogonal set on minus pi. So here we need to show that the following statement is true. That means 1 with cos x should be orthogonal, 1 with cos 2x, 1 with cos 3x, 1 with generally 1 with cos nx must be orthogonal. Similarly, 1 with sin x, 1 with sin 2x, 1 with sin 3x, and nx generally must be orthogonal. So individual must be orthogonal function on the given interval. So starting from 1 with cos nx, let's look at what 1 cos nx you mean. The inner product 1 cos nx is defined based on the comprehensive definition from minus pi to pi, because we are working the orthogonality on this interval. So this is the lower and upper limits here on the definite integral from minus pi to pi cos nx dx. So this is computed through the substitution technique, letting nx is t or any variable, any demi-variable. So I skip a big chunk of this work because this elementary to make integration. So we got sine nx over n, sine nx over n, finally as sine at pi, again at minus pi. Sine nx at pi is sine n pi, again sine minus n pi, sine minus of n pi. So sine n pi mean for n is just indexed formula. We have sine x, sine 2x, sine 3x, sine 4x. You mean that mean n is indexed from 1. That's why if sine pi is 0, sine 2 pi is 0 again, sine 3 pi is 0, sine n pi is generally 0. So sine minus n pi is again 0. Why sine n pi? You mean we have because it is just odd function. Sine of minus n pi is equals to minus of sine of n pi. So sine n pi is 0. Why? Because for we have sine of pi is 0, sine of 2 pi is again 0, sine pi means sine 180, sine 2 pi is sine 360, again sine 3 pi is 0, generally sine n pi, this is 0. Okay, that's good. So we have sine n pi is 0. Again, sine minus n pi is almost 0. I think it's just 0, not almost, just 0. So sine 0 minus 0 is 0 for all n, where n is clearly indexed from 1. That's why no restriction is needed. Similarly, for 1 with sine nx from minus pi to pi, sine nx dx, then we have minus cos nx over n from minus pi to pi. So again, minus of cos n pi. This would lead us to have because we have cos n pi is minus 1 to the power of n, sine n pi is 0, like we illustrated before. So we have minus 1 over n. That was the result of the definite integral, minus cos nx over n here. So that we assign specific value at n pi, again at minus n pi, minus 1 over cos n pi minus cosine of minus n pi. Again, cosine of minus n pi means cos n pi. Clearly, cosine of minus n pi, you mean cos n pi. Why? The function, cosine function in nature is even function. So that we have cosine of minus n pi. Cos n pi is here. Again, this is minus 1 over n. Minus cos n pi is 0. So 1 with sine x nx is orthogonal. 1 with any cos nx. That means 1 with specifically with cos x, with cos tx, with cos 3x, generally with cos nx is orthogonal. Similarly, 1 with sine x, sine 2x, sine 3x, generally with sine nx is also orthogonal. This means with the cos nx with cosine function with cosine function. Okay. So this is obtained through the definition of inner product. Cos nx, that might be setting as f and g, so f times g dx, cos nx with cos mx dx. It's not hard to integrate here. You can use the trigonometric identity, cos nx cos mx. That means here this is cos a cos b, cos a plus b plus cos a minus b over 2. That's why instead of okay, good, we have instead of cos nx, this may be a, this may be b, then cos a cos b, instead of cos a cos b, we mean cos a plus b plus cos of a minus b. So we just want to be pledging inside this expression via the trigonometric identity. So nx mean a, mx mean b, so cos of a plus b plus cos of a minus b over 2, like we did here. So 1 over 3 is free of the integration, so that we move out of the integration here. Then you apply termwise integration, cosine of n plus m of x. You mean integration of this, you mean you use substitution technique. Okay, you simply let u is n plus m of x. Okay, so that du, you mean du is n plus m, then dx. So instead of dx I can use, okay, du over n plus m. That's the substitution. So that we have this form, sine of n plus m. The same thing, you can also apply the same procedure for the second term, so that you use termwise integration. Sine of u, you mean here cos u, integration of cos u, you mean sine u over, and instead of dx you mean du over n plus m. N plus m is free of the integration, so that you can move out. That's why we have this denominator. Again, we have also n minus m as a denominator for the second termwise integration. Finally, apply the assignment at x equals to pi, again at x equals to minus pi. Clearly, since n and m are integers, sine of n pi is 0, we said. Okay, in the previous we have sine n pi is 0, sine n pi is 0, which are here. Okay, sine n pi is 0 for any integer. For any integer we have sine n pi is 0. So because this is an integer, n is integer, m is integer, n plus m is integer, again n minus m is an integer. So sine of an integer at pi, we have x is pi, again pi. Before you go to this value, we have pi here. Sine of n plus m pi, you mean sine of any integer times pi, you mean, that's in it, not multiplication. Sine of n plus m pi, you mean sine integer pi, you mean 0. Similarly, sine integer n minus m is some arbitrary integer, then pi is 0. Minus, you go with this sine of n plus m of minus pi. If you just want to be pledging inside x minus pi, due to sine function is odd function like we did before, still we got 0. Sine of an integer of pi, sine of minus n pi of at minus pi again is 0. But clearly n minus m should be not 0. That is, n is different from m. Okay. But if n is m, you mean from the integration, if n is m, cos n minus m means 0, cos 0. But here is cosine function, integration of over minus pi to pi of cosine function, outcome at 0. But we have cosine of n minus m is, in this case cosine of n minus m is 0. Because n is m, we said cos 0 is 1, integration of cos 1 dx, you mean x. Okay, x over 2, integration of x over 2. We have this. Let me tell you something here. If n is m, you mean from minus pi to pi, cosine of 2nx. Okay, plus cosine of 0 dx finally. Okay, over 2. So this integration, you mean, let me make it half. Integration of cos 2nx mean sine of 2nx, because n is m, that's why we use 2n, plus cos 0 is 1, integration of 1 with respect to x mean x. okay, at pi, again minus pi. Sine 2n pi is 0, sine minus 2n pi is 0. So the first term is just vanished. Remains with half of at x is pi minus. At x of minus pi is minus pi. So it turns to plus here, plus. So this is pi plus pi is 2 pi over 2 is pi human. Okay, so they are orthogonal if n is different from m. If n is m, could not be in orthogonal human. That's why we have specified this. If n is m, like we illustrated here, obtained with pi, that means could not be orthogonal. So cos nx with cos mx is again orthogonal. Sin mx with sin nx again. Let's look at sin mx with sin nx. The same procedure can be adopted like we did before. We apply the inner product of two function, letting f here, this is g, so that from minus pi to pi, sin nx, sin mx dx. Again, this is obtained via trigonometric identity, that is sine with sine, you mean sine a sine b mean cos a minus b minus cos a plus b over 2. That is, if this is a, this is b for the time being. So that's cos a, I mean sine a sine b under the integrand is computed through cos a minus b minus cos a plus b over 2. That's why we have cos a minus b minus cos a plus b human, okay, through the trigonometric identity. So you apply termwise integration. Half is independent of the integration, so that we move it out of the integration half. So termwise integration can apply integration of cosine, you mean sine of n minus m over n minus m of x minus, again this is sine of n plus m over n plus m, like we did before. You apply the substitution technique. For n minus m is n minus m of x is u, okay, n minus m of dx, you mean du. Okay, that's very interesting. Again, exceedingly elementary to apply the substitution technique. So we have dx is du over nm. So instead of dx here, du over nm for the term-wise, the first term. Again, for the second, we use n plus m is u, so that dx is du over n plus m can be resulted. So that we got this. Due to the idea of n minus m is an integer, n plus m is an integer, sine of an integer times pi, I mean of pi, again sine n plus m of n plus m of pi is 0. Because for any sine of n pi is 0, where n is an integer. But clearly n should be, n minus m is not 0, okay, n minus m is not 0. That means n minus m is not 0, n is different from m. N minus m is not 0, so m is different from, this is m, okay, should not be confused with my handwriting. Alright, something interrupted us in our lecture. It doesn't matter, we will be rectify it next. And but if n is m, you mean cos 0 is 1, like we did before, so that we got pi. That's why it cannot be orthogonal at f n is equals to m. So we skip that work. Though we only concerned that for n different from m, the two functions sine n with sine mx is orthogonal. Similarly, cos nx with cos mx, and we apply the inner product, definition of inner product, f and g from minus pi to pi, cos nx sine n mx dx. So that's cos with sine, cos a sine b. You mean here sine of a plus b minus sine of a minus b over 2. So this is easily computed through the trigonometric identity. You can derive the formula of this. They are elementary. So that we get, instead of cos a sine b, you mean sine of a plus b minus sine of a minus b. So we have sine of n plus m of x over minus sine n minus mx over 2, the grand over here. Half again move out of the integration independent of the integral, and this integration, termwise integration, mean using substitution technique, letting n plus mx is as usual. We get minus cos of n plus m of x over n plus m plus cos of n minus m of x over n minus m. Similarly, you assign a specific value at pi, again at minus pi. Cosine of n plus m pi, you mean from this we have cosine of n plus m. This is an integer, this and this is an integer. So that, let's say if you assign at x equals pi, we have minus of minus 1 the power of n, again plus minus 1 the power of n. Okay, this is an integer. So minus of cosine of an integer of pi is, because we have seen that cosine of n pi is minus 1 the power of n for any integer. That's why minus cosine of n plus m is minus of minus 1. This is 0 at pi. Similarly, at minus pi, d2 cosine function is even, minus cosine of because cosine of minus n pi is similarly minus 1 the power of n. So that even at minus pi we have minus 1 the power of n. Okay, so plus minus 1 the power of n. So this is 0 for all n and m. Even if n is equals to m, sine 0 is 0, so integration of 0 is some constant, at pi is constant, again at minus pi is that itself, then 0. You mean they are orthogonal everywhere. So generally we have this expression minus L to L, cosine of n pi x over L is here, again sine function. These are the eigenfunctions on minus L to L, not specific